Wasabi, you guys. Silver here, and this is Integration Bee Training for Advanced Part 3. Finally, we're in the third section where we will be learning ninja substitution. Now, let me first show you what on earth is ninja substitution. So ninja substitution is when we let u equal negative x. This is what I call ninja substitution. You're probably thinking, okay, but why are we just a negative? Like, that's it? Like, why are we doing this? So usually we'll come across, let's say, I guess a good example. Let's say, like, if we have something like this, right? And we have, let's say, some function like f or g. Something like this, right? And then let's say that the function has a property where if we do negative x, then this is equal to g of x, and vice versa. And so when we do u equal negative x, of course the bounds they don't change, and the reason is because, I mean, let u equal negative x, you get like a and negative a, and of course when you do du, we have du, you get negative dx, and of course this negative, it'll just rewind the bounds back together, back to normally. So because of that, the bounds stay the same, and then of course f of negative x gives us g of x. G of x. G of negative x is f of x. Aha, do you see where this is going? So it is like King's rule, pretty much. The only difference is it's just a negative. So I find it a lot easier than King's rule, but it's not very common because it's not straightforward as King's rule. The substitution is a lot easier than King's rule, don't get me wrong, but the way the integrals that you will be given in competitions, it will throw you off a lot. So I wouldn't say that it's a lot easier, but you just have to get used to a lot of you just have to get more comfortable as you go through this video. Okay, but you can easily see that when you add these two together, this comes out as a half negative a dx 1. This is 2a. This is going to give us a, right? But be careful. This is I'm just giving you an example of how ninja substitution can be useful. A lot of the times in ninja substitution, you will not come across this. It is going to be a lot more complicated, a lot more algebra manipulation. So, and that's what we're going to go through in this section. So let's start with a beginner level ninja substitution. So how do we apply this? Right, of course, you're looking at it right now. This does not look like what I showed you, right? It's not always a King's rule format. Sometimes, well, the most common integral form for ninja substitution is we get exponentials like this. So we see we have x squared 1 plus e to the x dx. Okay, interesting. How do we solve this? Right, so we're going to do u equals negative x. Okay, I'm going to color this yellow. Alright, so of course x squared remains the same, but then we get 1 plus e to the negative x. Now you're wondering, okay, but how does this make this any better? How does this make this any much better? Well, we have e to the negative x. What do we always do in algebraic manipulation? If you remember your intermediate training, we multiply top and bottom by e to the x, and we get e to the x plus 1. Alright. Now this is a little hard to see if you've never seen this before. But what happens if we add these two together, you know? This is I. If this is equal to I, then this is also equal to I. Because this is equal to this, okay? Remember we just did use substitution. If you remember how, you know, interchanging variables doesn't really matter in definite integration. So now, we have I, 2I is equal to -1 to 1. The denominator is the same. But now we have x squared plus x squared e to the x. Aha, and what do you notice? We could factor out the x squared. Okay? And then when you factor out the x squared, we get 1 plus e to the x, 1 plus e to the x. This just cancels out. So we actually have, let me just go ahead and just solve for I. Right? Here, you could literally just go straight into symmetry. You could possibly do that in your head, actually. And you'll notice that this equals 1/3. And that's our integral. That's our answer. The integral is 1/3, and that's how you do ninja substitution. Again, the process, it's actually it's quite nice. It's satisfying. It's not so difficult, right? You just have to determine odds and even functions. That's it. But it's not the look of the integral does not look straightforward. That's all I'm just kind of warning you about. So it just takes a lot of comfortability to get used to and recognizing when to use ninja substitution. Now this looks daunting. Don't get me wrong. This looks daunting. We got 1 plus x squared. Okay, maybe trig substitution. You might think, oh, let x equal tangent theta, right? Negative pi over 2 negative pi over 2 to pi over 2. But then we have this e to the x here. Huh. So we'll just end up getting 1 plus e to the tangent. 1 plus e to the tangent of x. Or tangent theta. But, you know, that doesn't really help. How like, what's going on? What do we do? Right. So, of course, Trig-Sub's not going to help, unfortunately. But what will help is ninja substitution. Let me color this in yellow so that you get comfortable. That u equal -x. Then of course the bounds don't change. I know I'm going to be okay because we have -infinity to infinity. So thankfully, when I do ninja substitution, it doesn't affect the bounds. du, and then 1 plus x squared, 1 plus e to the -x. And of course, like, I don't know why I put u, I just noticed. But here, algebraic manipulation, we could just multiply top and bottom by e to the x. And just like that. And now you're probably noticing, if we add these two integrals together, right, from -infinity to infinity, we go ahead, and so we got 1 plus e to the x, dx, and then we, of course, the denominator is still the same, and this cancels out. So what we have now is I equal to half of from -infinity to infinity dx 1 plus x squared, right? Of course, we just use symmetry, and you can easily see that the answer to this integral is pi over 2. Ninja substitution is very nice. It's very helpful. You'd be very surprised how helpful this is, actually. Okay, what on earth is this? This looks awkward, right? This looks very awkward. This, if you saw this not knowing what ninja substitution is, you would have been thrown off. You would have just been just hesitant, just looking at that, not knowing what to do, right? But don't freak out. Don't freak out. Let u equal negative x. That's all it does. That's all you got to do. So now bounds don't change. Cosine of x is an even function. And then 1 plus e to the negative 1 over x. Alright, very nice. But then now what? Well, of course, with exponential cases like this, what do we always do? We just multiply top and bottom by e to the whatever we need. So, in this case, e to the 1 over x plus 1, just like that. And you can already easily tell just by, the amount of times we've been going over this. 2y, 1 to 1, you can easily see, you're probably already knowing, like you're doing it mentally, you could already see that the denominator cancels out. But I'll just write it out just in case for some others. 1 plus e to the 1 over x. The denominator stays the same. You can see that this cancels out. And so now what we have is just cosine of x dx. Of course, use symmetry, and you already know that the whole integral for this, the answer, is just sine of 1. And it's actually pretty fast too, right? The more practice you start doing with ninja substitution, you can easily start integrating mentally, because it's actually not that much steps, really. So it's very nice. It's very, very helpful. This is very interesting. X squared over 1 plus x to the power of 2x. Huh. What do we do with this? This is a little intimidating, but don't freak out. What is something sus about this integral? Something sus is we have, we have bounds from -2 to 2. Very sus. And of course, we can actually reform this as 1 plus x squared to the power of x. Okay. And just kind of like think about it. What would it look like if you were to do u equals negative x? If we were to change this to negative x, well, this won't change because it's being squared. This won't change because it's being squared. But then we have a negative x here. That's the only difference. So when we do u equal negative x, it's going to look like this. Negative x. Okay, we have a negative x here, but now what? Well, just do what we usually do, right? Just go with the flow. I don't know what I'm doing, but what would happen if we were to, do what we do as usual? What if we do the algebraic manipulation, multiply top and bottom by x squared? So multiply top and bottom by x squared. We have x squared. I'll just write, I'm sorry, not just x squared. X squared to the power of x. Okay? Don't get fooled. X squared to the power of x plus 1. And this should be 2. I'm sorry, that should be 2. Okay. And now we have this. Now, we'll go ahead and dive straight into just adding these two integrals together. Of course, we're going to get a half if we're doing 2y. And then here I see we have x squared plus x squared, x squared to the power of x, plus x squared to the power of x plus 1. of course, you can factor the x squared out, right? And we know that the denominator is going to be canceled out. So we just go ahead and just speed integrate that. We know it's going to be x squared dx. At this point, you can just use symmetry, right? We end up with from 0 to x squared. This is equal to 8/3. For those, if I went too fast, you know, algebraically this, you factor out x squared, you pretty much have this. And it just gets canceled out. We just factor out the x squared. Just for those who, if I went too fast. But, yeah. Very, very easy. Okay. Again, it's like a lot, as you can probably notice a pattern here. When every time we use ninja substitution, we apply it to not only just because of the bounds, but because we have this exponent here, this exponential part of the function. That is what really helped us simplify things a lot further. That's what helped us cancel out the denominator a lot when we apply ninja substitution. Okay? This looks weird, right? It looks a little ugly, just a little ugly. That this exponent to some rational function looks a little bit scary, but let's not worry. Let's calm down. We notice something sus, right? What is sus about this integral? The bounds, and that we have this exponential type of function. And not only that, it's usually a lot of the times we get things like f of x, where this is an odd function. A lot of the times we get things like that. If it was even, then we're kind of screwed. You can't use ninja substitution. But if it was odd, an odd function, then we can do ninja substitution, and then the algebraic manipulation will help cancel out. Just kind of giving you that pattern recognition. So u equals negative x, bounds, the bounds just not going to change, dx 1 plus e x squared is itself, but then we have negative 4x. Alright, sweet. And now this is equal to e to the 4x, x squared minus 1 dx. And then, of course, technically the denominator just doesn't change. Right. And of course, just looking at this, and here, right? Let this equal to I, let this equal to I. You can immediately see right away that when we do 2y, it's just going to cancel out. It's just going to cancel out. This is just going to become 1 dx, negative 1 to 1. Right? And you're literally done. Right? So that's it. This is just going to equal to 1. Alrighty, this is our last integral. And of course, what do we do here? I noticed that we have a negative to positive bound, so that's a little suspicious. And I see we have a negative to deal with. Okay, so let's go ahead and apply ninja substitution. Right, let u equal negative x, we get e to the negative x plus 1. Interesting. Huh. Okay, well let's retreat a little bit, because I don't think that's gonna give us the same integral. Or will it? Well, let's kind of simplify this further to see what is going on and what we need to modify. So of course we have, this is x squared plus 2x plus 1. So negative x squared minus 2x minus 1. Okay. And then we have 1 plus e to the negative x dx. What do we do here? So, I mean, this is 1 over e to the negative x squared minus 2x 1 plus e to the negative 2x dx. Interesting. What do we do? Oh, okay, we have negative 2x here, negative 2x here. Algebraic manipulation. Okay. And what I mean by that is we're going to multiply top and bottom by e to the 2x. So we get e to the negative x squared, e to the 2x plus 1. If we do u equal negative x, then it will work. How do I know that? A lot of the times what I've been showing you, if you notice from all the previous integrals we worked with, we have an even f, even function, 1 plus e to the odd function. Right? And when we apply ninja substitution, we get an even, and then of course 1 plus e to the negative odd. Right? But then we also know that, of course, because of algebraic manipulation, right, multiply top and bottom by e to the odd function, we get e odd function here. And then when we add these two integrals together, we get 1 plus e to the odd, 1 plus e to the odd, they cancel out and we just left with an even function. Right? This has to be even, otherwise if it was odd then we would have a negative, and that screws everything up. Then we'll get something like 1 minus e to the odd of x when we add two integrals together. So that's why it's crucial that we need this function to be even. So the majority of the times we've just been integrating functions like this. So, but that's just the beginner lesson in this section. This is just me introducing you to ninja substitution. In advanced cases, it would not look like this. We would have to do much further algebraic manipulation. But for now, in this section, this is what we've just been doing. Okay? Alright, so that's what we've been doing. Now, is it a good time to apply that here? Is it a good time to apply that here? Yes, because we have an even function, we have an odd function at the exponent, and we have a negative to positive of the same whatever in the bound. So now, let u equal negative x. This doesn't change. And we have 1 plus e to the negative 2x. I just decided to put it here. And then this is also equal to 1 over e to negative x squared, e to the 2x. And of course the denominator does not change like that, right? So of course because of that, we add two integrals together, we get 1 over 2e. And of course they cancel out. We can easily see that. 1 plus e to the 2x. That matches the denominator. And so now symmetry, 1 over e. Oh, we already know what this is from our intermediate training, right? Do you remember? This is the Gaussian integral. You must know this integral. It's very common. And so our answer is the square root of pi over 2e. This is our answer. Okay? And that's it. That's it for this section. you just have to get used to it. You might just have to get comfortable with it. So highly recommend just rewatching the this whole video and then trying the integrals on your own so that you get more comfortable with it. Okay? Alright. I hope this helps. Thank you so much for watching, and I'll see you guys in the next section.